Last but not least, let's look at the equation of a line in 3 dimensions. But first, let's look at the 2-dimensional case. Now, for a vector equation of the line that passes through the point 1, 5, so let's find this point here. So let's make this 0, x, 1, 2, 3, 4, 6, 7, 8, 9, 10, etc. 1, 2, 3, 4, 5, 6, 7, 8. That's y. So our point is 1, 5. It's here. 1, 5 is parallel to the vector 3j. So I'll just put our vector here. So 3 minus 2. So our vector looks like this. That's our v. Now, firstly, let's consider the position vector OP. There's our position vector. So our position vector OP is 1, 5 minus 0, 0. So we've got 1, 5. What if we take our vector v and we start it instead at the tip of OP? And what if we take another copy of v? And let's say we took another copy of v. Do we see that by adding multiples of this vector, we are creating or mapping out a line in 3D space or in space? And if we did the same vector but multiply it by a negative, so we would be going in the opposite direction. So here, so we're essentially hanging one here, hanging one there, and left with a line in the air. Essentially, any point upon this line, so let's take this point here. This point here is in fact x, so 7, 1. Okay, that's a position vector here. So the position vector to x is the position vector for P, OP, plus, if you look at it, is in fact adding the multiples of V. So this plus this is equal to this one. So it's actually t outside of 3 minus 2. Or we could do is equal to OP plus TV. This here is a scalar multiplier. T is just a scalar multiplier. Okay. Now, if we look at this, this is in fact OX is equal to, OP is 1, 5. So we have 1 plus 3 times by t for our x, and our y is 5 minus 2 times by t. And if we look at this point here, t, well, when x is equal to 7, this is 1 plus 3t. So t in this case is equal to 2. And y is 1, which is 5 minus 2t, giving us t once again is equal to 2. So it's just multiplying by a value. Okay, and you can find any point along the line simply by changing t. So if we let OP be the position vector of a given vector on the line, here OP is 1, 5, or I plus 5j. And you recall that your vector is 3 minus 2, tells us the direction of the line. We add scalar multiples of v onto OP to get us to another point on the line. So you can say x is another point on the line, x, y, so it's actually a vector here. If t is a scalar, then the position vector x can be written as OX is equal to the position vector for OP plus t times by v. This is called the vector equation of the line through the point P in the direction of v. So in our example, we had OX is equal to 1, 5 plus t, 3 minus 2, and we can expand that out. So xy is equal to 1, 5 plus that. So in components, we have 1 plus 3t, and y is equal to 5 minus 2t. These are the parametric equations of the line. So something to think about. If we have OX is equal to this, find any two more points that lie in that line. To find any more points, we simply just put in different values of t. So x1, when t is equal to, say, 2 or 3, since we've already done 2, is going to be 1 plus 3 times by 3. And y1 will be 5 minus 2 times by 3. So we have 10, and this one is 5 minus 6, so it's minus 1. Okay, and if we take another value of t, let's take t, so this is t equals to 3, why don't we take t equals to minus 2? We have 1 minus 2 times by 3, so we've got minus 5, and 5 minus 2 times by minus 2, so it's actually going to be 9. Minus 5, 9. How could you test whether or not a given point lies on a given line? To test how a given point lies on a given line, you need to see whether or not that point gives a unique value of t. So if lies on the line, the point has a unique value of t. For example, does 10, 3 lie on the line? If we put this in, x is equal to 1 plus 3t, y is equal to 5 minus 2t. So 10 is equal to 1 plus 3t, which gives us 10 minus 1 divided by 3 is 3. And when we put in 3, 5 minus 2t, we get 3 minus 5, so that's minus 2 divided by minus 2, t is equal to 1. This means that tx does not equal to ty in this case. So 10, 3 does not lie on the line. This can be extended to the 3D case. So the parametric equations of a line in 3D that passes through the points x0, y0, z0, and whose direction is given by the vector ABC are x is equal to x0 plus at, y is equal to y0 plus bt, z is equal to z0 plus ct. And if we eliminate t, so what this basically means is rearrange for t over a is equal to t. So y minus y0 over b is equal to t. And z minus z0 over c is equal to t. We get the symmetric equations here. So that gives us three equations. The vector equation of the line, parametric equations, and the symmetric equations. Now, finding distances in 3D, we've already done this in a previous lecture, but we won't have time to develop all the methods in the lecture, so it's optional material for this semester, these topics that I'm about to list, and will not be tested in the mastery test nor in the final exam. So here's an optional challenge. Explain in your own words how these distances can be calculated. Think of projections. Try to invent the formulas yourself before looking at the textbook. So, distance from a point to a plane, distance from a point to a line, distance between two planes, distance between two lines. And look at the scalar and vector triple products. These are also optional material and not examinable this semester. See you next week.